Okay, students, unfortunately today we were not able to conduct our lecture because of problems with our equipment. However, as promised, I have attempted to voice annotate my slides for this lecture, lecture number 7, as promised. So here goes. So we'll continue with our thermodynamics and electrochemistry. Okay. Well, from the last lecture we were looking at the second law of thermodynamics, and this was the law. This is the law that speaks about entropy change of a system and relates entropy change of the system to the heat in that system and also the temperature. Now, the entropy of an isolated system increases when a spontaneous change occurs in the system, or you could say then that spontaneous processes takes place when there is a change from low entropy to a state of high entropy. A matter of fact, you could say then that is the earmark, that is the characteristic of a spontaneous change. But note that we have underlined isolated system, because for the entropy criterion to be applied to a system being a chemical reaction or so, the system must be isolated. And here we're saying that for an isolated system with entropy change being greater than 0, we can say that such a change or such a reaction is spontaneous. However, if the entropy change of that system is less than 0, then we say that the change is non-spontaneous. If the entropy change of that isolated system is equal to 0, then the system is at equilibrium. Alright, and these are some characteristics that you have to bear in mind. Continuing our recap from the last lecture, now if we try to apply the second law to perfect gas processes, right? Now recall the definition for a reversible process. Alright, so these occur with the system at equilibrium, reversible process. Remember, a reversible process is at equilibrium at every point. Hence, PV, if you're dealing with a gas, PV is equal to some constant, and that constant is nRT. Now, for a system at equilibrium, we just said on the previous slide that entropy change must be equal to 0. Now, the question is, does the entropy criterion work for isothermal reversible processes in a perfect gas? Isothermal reversible. Now, once you hear reversible, you know that this means that a system is at equilibrium at every point. So clearly it cannot have entropy. Alright? Cannot have entropy, because remember we said that at equilibrium entropy change is equal to 0. Alright, so there can be no entropy change for a reversible system. Alright, let's try to prove this. Now, isothermal reversible process. Now, delta S is equal to Q reversible over temperature. Now, remember that for isothermal process, delta U is equal to 0. That is, there is no change in internal energy. Alright, we are not saying that there is no internal energy. There is, but there is no change, so it's constant. And hence, minus Q is equal to W. Right, so heat released is equal to work done, and this comes from the fact that delta U is equal to Q plus W, which is the first law of thermodynamics. Now remember, we also proved that work is equal to minus nRT ln V final over V initial. Now if work is equal to that, then the negative of work will give us Q, and if we divide Q by T, we end up with entropy change, and hence we have a formula here for entropy change. Now, that is surprising, because we expect that entropy change for a reversible process would be 0. In other words, that formula should work out and show us that delta S is equal to 0. What is the problem? Now, we did not carry out our analysis on an isolated system as is required for application of the second law of thermodynamics. the entropy criterion only works when you have an isolated system. So that was our problem. Now let's look at how we can convert our system to an isolated system. Now all you have to do, if you have your system and you, of course your system is in some environment, that is, it has some surroundings. Now if you consider your system plus its surroundings, then you can put those two together and classify that as an isolated system. So system, entropy change of the system plus the entropy change of its surroundings is equal to isolated system. So clearly, if you could find the entropy change for your system, which would be like your reaction, and the entropy change for the surroundings of your reaction, and add those two, sum those two, then you will get the entropy change for an isolated system. Now we just showed that the entropy change for the system could be nRT ln V final over V initial. Clearly, any increase, remember that the system is in its surroundings, any increase in entropy of our system will result in a decrease in the entropy of its surroundings by the same magnitude. However, it's a decrease, and so it is negative. Okay? Similarly, you could say that any amount of heat energy released by the system is equal in magnitude to the amount of heat energy gained by the surroundings. However, the sign will be positive because the surroundings gain the heat energy, whereas the system would have a negative sign for its heat energy because it lost the heat energy. Hence, if you think about it like this, what you will find is that the entropy change for the system being the same in magnitude as that for the surroundings. However, for the surroundings it would be negative. It would be like saying plus x minus x. Hence you will end up with 0 as your answer for the entropy change of an isolated system. And that is a proof that for an isolated system, at equilibrium, entropy change is equal to 0. Great. Now, about what we want to do in this lecture. Now we want to apply the second law to perfect gas irreversible processes. Now remember what our irreversible process is, or irreversible system. It's a system where PV is not equal to a constant all throughout the system. In fact, PV is only equal to a constant at the beginning and at the end of the process. Right? But in between the beginning and the end, the system is not at equilibrium. PV is not equal to a constant. And we proved, I think in lecture 6, that work for such a system is equal to, work done by such a system is equal to minus P delta V. And even our tutorials of last week, we showed this. Now, for an isolated system, not isolated, for an isothermal system, remember that delta U is equal to 0, and hence minus Q is equal to plus W. However, this, since we just mentioned that the work of such a system is equal to P delta V, then we could replace W, which is work, by P delta V. So heat loss is equal to the work done on the system. Now, in finding delta S, from the second law of thermodynamics, in finding delta S, we see where we have to take the ratio of Q and the temperature. Now remember that the work done is the positive of the heat released, same magnitude, different signs. And so you find that you could actually calculate the entropy change for the for irreversible process by actually dividing. You can actually divide the P delta V by T. Now, remember that for the system, which would be the reaction, the work or the heat loss is not equal to P delta V. In fact, for the system, which is the reaction, Q is equal to nRT ln V final over V initial. Remember, that's Q. but W is equal to minus nRT ln V final over V initial. Now, for the surroundings, you could actually calculate Q using minus P delta V. Alright? Q, which is the positive, that is heat absorbed, is equal to work done by the system, hence it is minus P delta V. Now, why is that? Now, the basis for this notion is the reality that at constant temperature and constant pressure, surroundings like the atmosphere has such vast internal energy that the equilibrium for the surrounding is not disturbed by heat or work done in a finite system. So for the surroundings, the heat energy can be calculated from minus P delta V. Right? You don't have to use nRT ln V final over V initial. You use that for the system. But for the surroundings, you use minus P delta V. Okay. Now, seeing that we are able now to calculate the heat for each situations for the system and for the surroundings, then of course we can calculate the entropy change for both. Alright? We can calculate the entropy change for both by just dividing the heat by temperature. And here we have it. Alright? Entropy for system, nRT ln V final over V initial, whereas the entropy change, right? Entropy change for the entropy change for the system, there it is, nRT ln V final over V initial. Whereas the entropy change for the environment or for the surroundings then would be minus P delta V over T. And here we have an isolated system. And that's how you would work with your system. Now let's look at an example. Let's look at an example. For example, a reaction of hydrogen gas with oxygen gas to produce water. The standard enthalpy change for such a process is equal to minus 285.8 kilojoules. Right? So that is our standard enthalpy change for this reaction. Now this process is spontaneous. We know this for a fact because oxygen and hydrogen react explosively with each other to produce water once a spark is introduced to supply the minimum activation energy to start off the process. Now the good thing about entropy is that absolute entropy values are available. Absolute entropy values are available in that you could get the entropy for just water. You don't have to think about just an entropy change. You have absolute entropy values. And you could get these from tables. So for example, if you want to calculate the entropy change for the formation of water, then you can get the entropy for water. Of course, you'll say products minus reactants. Of course, considering the coefficients. So let us do that calculation. Now the entropy for water is 70 joule per Kelvin per mole, whereas that for hydrogen gas it's 130.5 joule per Kelvin per mole, and of course you have to sum that with the entropy for oxygen, and of course you have to multiply the oxygen by 0.5 because you only have half a mole of oxygen, and so you will end up with an entropy change of minus 163.2 joule per Kelvin. Now, such an entropy change indicates that the reaction is non-spontaneous. Now, from experimentation, we know that this is not true. The reaction is actually spontaneous. But what is the problem? What is the problem? Alright? What is the problem? Why is it negative? Because remember, negative entropy means that the process is moving from a state of high entropy to low entropy, such that when you say final minus initial, you end up with a negative, and that is not how spontaneous processes behave. What is the issue? Now, clearly you would realize that we did not consider the environment. We did not consider the environment or the surroundings, if you want to put it like that. And that is the reason for our entropy being negative, indicating that the reaction is non-spontaneous, which is contradictory to what we know. Now, of course, entropy change of isolated system is equal to system plus surroundings. Now remember, the heat lost by the system is equal to the heat gained by the surroundings. So if the enthalpy if the enthalpy change for the system is minus 285.8 kilojoules, then the enthalpy gained by the surroundings is the same magnitude as that but opposite sign, and hence we multiply 285.8 kilojoules by minus 1 such that we end up with a positive value. And of course we are converting here the kilojoules to joules by multiplying it by 1000 and then dividing by 298 Kelvin to get the entropy change of the surroundings to be 959.1 joule per Kelvin. Now of course when we put the entropy change of the system and the entropy change of the surroundings together, we have now the isolated system, the entropy change for the isolated system, which works out to be 795.9 joule per Kelvin. And this is a positive entropy value indicating that the reaction is indeed spontaneous, as in keeping with observations from experimental data. So what is to be taken from this? In using entropy to discuss spontaneity, you have to consider changes in the entropy of the system and also changes in its surroundings. Now let's look at a new criterion for judging spontaneity, and this is called the Gibbs energy, which was developed by Josiah Willard Gibbs, an American scientist, some time ago. Now, entropy, was a criterion, but we had to consider the environment. It was a good criterion, but it's too much work. So let's talk about what we call a Gibbs energy. Gibbs energy. Now, if the Gibbs energy is negative, Gibbs energy for a reaction, if that is negative, then the reaction is said to be spontaneous. If the Gibbs energy is positive, that is, it's greater than 0, then the reaction is said to be non-spontaneous. Now, if the Gibbs energy change is equal to 0, however, then the reaction is at equilibrium, and the Gibbs energy can be calculated from this formula. Delta G is equal to delta H minus T delta S, and that is the formula that you use to calculate the Gibbs energy. Now, where did the Gibbs energy come from? Now, think about it. Entropy change of isolated system is equal to entropy change of system plus surroundings. Alright? Now, for chemical reactions taking place under standard conditions in surroundings at constant temperature and constant pressure, you could write delta S isolated is equal to delta S of the system minus delta H of the system over T. Right? Because remember, once we're working on a constant pressure, Q is equal to delta H. Right? So you could replace Q with delta H and divide that by temperature to get the entropy. It is the same thing as the entropy, and that is for the system. And why we put system? Why do we have system over here? Because remember, the entropy for the surroundings will be, related to the enthalpy released by the system or absorbed. Same magnitude, different signs, and that's how we can write this. Now, as you'll realize, if we could just multiply by minus t, then we'll end up with this third equation here. Now, the minus t delta S of the isolated system, if you think about it, that kind of makes things simpler, and we call this the change in Gibbs energy. We call that the change in Gibbs energy. And so with a little bit of rearrangement of this third equation and the conversion of minus t delta S, changing t delta S isolated to delta G, we have the formula for calculating Gibbs energy. Now, let's try to make use of this. Let's try to apply this. Let's try to see how this works. Okay, the enthalpy change, standard enthalpy change that is, for the formation of water from oxygen and hydrogen is minus 285.8 kilojoules, as we mentioned before. We also calculated the entropy change for this process, the standard entropy change, and we got minus 163.2 joule per Kelvin as before. Now, if you should plug those two into the formula for calculating Gibbs energy, and remembering that we're working under standard conditions, So the temperature is 298. Then you will get a Gibbs energy value of minus 237.2 kilojoules. Alright? And the fact that this value is negative, as mentioned earlier, indicates that the reaction is spontaneous. Alright, and so you find that the Gibbs energy criterion is quite easy just by knowing the enthalpy and the entropy and the enthalpy change and entropy change and the temperature. Then you could calculate the Gibbs energy, and that could allow you to determine whether or not the reaction is going in a spontaneous direction, alright, or if you have a spontaneous reaction occurring. Of course, you could summarize this entire type of thinking in the form that you can see here, that delta H of reaction, if it is positive and delta S is positive, then reaction is spontaneous at high temperatures. However, if delta H of the reaction is negative and the delta S of the reaction is positive, then the reaction is spontaneous at all temperatures, and so on and so forth. And that is just a summary. Now, you could use the Gibbs energy formula to determine the range over which a reaction might be spontaneous. For example, water. Let us consider the same reaction, water. All you have to do firstly is to equate the formula for calculating Gibbs energy. Equate that formula to 0. So you are setting the system at equilibrium. And then calculate at what temperature will the system be at equilibrium. So in other words, you say, okay, delta G is equal to 0. So you have delta H is equal to minus T delta S is equal to 0. Alright, so delta H minus T delta S is equal to 0. And you put your enthalpy change value and your entropy change value. And the temperature, you don't know the temperature, so you'll just rearrange, change subject of formula, and calculate the temperature. Now for this reaction, we calculate that the temperature would be 1751 Kelvin. Alright, this temperature is where the reaction is at equilibrium. Now we are not interested in equilibrium, we are interested in the temperature range over which the Gibbs energy will be negative. That is the temperature range over which the reaction will be spontaneous. That is what we are interested in. Now, all you have to do is just to think to yourself. Right? Think to yourself. Is it that above this temperature, which is the temperature I'm talking about is 1751 Kelvin, is it that above this temperature I will get a negative value for delta G? All you have to do is to say use 1752 and put that back into the formula. Put it where T is. Use 1752. Put it where T is and calculate. If you get a negative value, then the reaction is spontaneous above 1752. However, if you get a positive value, it means that the reaction is spontaneous below 1751.